like, if you looked at some kind of density matrix for the state, it would look thermal, okay? And this is how Hawking radiation comes about. If you look at what the density matrix of the state looked like from the point of view of, if you look at the density matrix just for the outside of the black hole, it's thermal, okay? And there's one more important difference. Yeah, so if you look at beta in this case, I think I wrote it down before, 4 pi times the Schwarzschild radius, okay? And as before, we can do beta proper, which, looking at the metric, we do rescale by a factor. So there's a square root of f to go to proper units, okay, proper time units. And near the horizon, f goes to 0, so the temperature blows up. But sort of crucially, far away, when r goes to infinity, f does not go to infinity like the Rindler factor did. F goes to 1, far away. So at infinity, there's still a finite temperature. So at infinity, the acceleration that you need to stay away from the black hole goes to 0. So you stop accelerating and you become an inertial observer, but you still see a finite temperature. Okay? So when you're far away from the black hole, even if you're an inertial observer, you still see sort of a finite temperature spectrum coming out of the black hole. And that's Hawking radiation. Okay? This is what tells you that the black hole evaporates, because there's a flux of energy at infinity coming out of the black hole. The flux of energy, and as promised, it's thermal with this temperature. Okay, and it has nothing to do with there's nothing about the black hole initial state in this at all. The thing that we used to determine the state was smoothness across the horizon. Okay, and smoothness across the horizon basically told us that there's information loss. Okay. So, unfortunately, I'm out of time. If I had a like.
Can you quantity there in your argument to remove the smoothness of the horizon?
Yeah. So what I mean by smoothness of horizon is that the infalling observer. Okay. So the long way to do it, right, is you basically. You choose, just like in Rindler space, we could choose different coordinates that cover like the left and the right or whatever. These Schwarzschild coordinates only cover the outside. That's like just looking at the right. Let me choose a different set of coordinates which cover, what happens when you fall through the horizon. Okay, that cover a bigger space. So the coordinates that would be appropriate for someone who's falling in. And then I ask, this person, what do they experience when they fall in? Okay, do they see very high energy quanta in their frame? Okay, kind of like the opposite of the Unruh effect, right? The Unruh effect said if we start in the Minkowski vacuum, then the accelerating observers see high energy quanta. Okay. Now I'm saying, I'm kind of asking the opposite question. What does, well, it's really the same question. What kind of quanta do the inertial observers see? Okay, do they see something or do they see nothing? And I want to say they see nothing in the same way that inertial observers in Minkowski space see nothing. And in the Minkowski space example, saying that inertial observers see nothing determined that the Rindler state was a thermal density matrix. In this case, saying that infalling observers see nothing determines, again, a thermal state. And because of the difference between the geometry of Rindler space and Schwarzschild geometry, you get something non-trivial at infinity. That's sort of like the only difference between Rindler space and Schwarzschild is that the effect doesn't go away at infinity in the case of Schwarzschild, because there's sort of this extra scale, this RF scale. Yeah. So the thing that happens next, and it would only take a few minutes, but I'd rather not rush it. The thing that happens next is we find a contradiction. Okay, there's a problem with this argument. Okay, if we think about it a little bit more, we find a kind of sophisticated contradiction with the strong subadditivity inequality. of quantum mechanics, okay, which tells us that something we did was wrong. This is the firewall argument. So, so tomorrow we'll pick up here. We'll look at I'll probably repeat what I said at the end here a little bit more carefully, and then we'll take a look at the different kinds of entanglements in the state. We've attempted to construct a state, and the state we've constructed has bad entanglement. If we think about it, it's inconsistent entanglement. It violates strong subadditivity. So then we'll go back and look at alternatives.
I have a quick question. So if I divided up space-time arbitrarily, rather than considering the richness of horizon, suppose I arbitrarily said that every field that is lying to the right is the right mover, and every field lying to the left is the left mover.
Yeah.
Why wouldn't I be able to associate a temperature on this surface?
So you would. So we're in Riddler space now, or we're in Minkowski space? Yeah, so the location of this Riddler horizon is arbitrary, right? You could just declare, I could have done the same decomposition somewhere else, right? And I would have gotten the same answer, okay? Anytime you can split the Minkowski space up into two halves in sort of any way you want. And you'll always find that one half looks thermal when you trace out the other half. Yeah. Yeah. So it doesn't matter where you decide to do the decomposition.
What you're asking, I think, was what happens if you just put a wall. Right?
Yeah.
If you put a wall, the problem is that the Hamiltonian does not act on a factorized Hilbert space. If you just put a wall, there are things on the left that can affect the right, and here that doesn't happen. So the Hamiltonian acts in a factorized way.
I mean, if there was actually something here?
He's just saying, say you just put a wall.
Like there's a physical.
Yeah, say right and left, and you quantize. You try to separate the modes. The problem is that there are things that can move from the left to the right. This cannot happen. This cannot happen here, right? In these coordinates, things from the left cannot reach the right.
Oh, you mean if I didn't do the division like with light cones?
Yeah, that's right. You speak the usual Minkowski coordinates and put a wall and divide them out.
If I instead do a division where my dividing surface was like this.
Yeah, exactly.
So this wouldn't work in the sort of quick. You need to specify what happens on the wall, basically. Even classically, right? If the sort of right space to the right of this wall is not, globally hyperbolic. So if we try to say what is the field here, you need to know data on this wall. So either it comes from over here or there's some theory on the wall.
Are there any other burning questions? Okay, if not, let's thank Stefan.